Okay, 4 by 4. We are in a 4-dimensional space, and it's symmetric. Symmetric, so how many components? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 components. So this was his main equation, which is called the Einstein field equations. What are these components, the 10 components of the kinetic energy Riemannian metric, such that the gravity will be lumped in there? The gravity due to the field of the sun gravitational field. So it has these G's will have the mass of the sun, the gravitational constant of Einstein, of Newton, everything. So he looked for G's. He tried to come up with expressions for these 10 components such that the gravity is inside. What does this imply? Like I said, this implies that a particle in gravitational field, a particle in gravitational field is simply free. But the space is changed, the space over which you are evolving. Remember, so he gonna solve these components of the G's and get the G's in terms of the mass of the sun, everything. These G's immediately give you the gammas. And these things are related to the curvature of your space, right? So over here, no gravity, we have flat 4D space. Time is longitudinal distance. That's fine. Over here, when you add gravity and you force the gravity term to go here as a part of your kinetic energy Riemannian metric or the Christoffel symbols, then your space is no longer flat. Your space is curved. And what dictates its curvature? Well, it's the mass of the sun that you used. So it's as if here is your space-time, and you put the sun, probably you haven't seen this video before, you put the huge mass on this sheet, then it bends your sheet. So the huge mass of the sun, according to Einstein, when it's put in the world, it bends the space-time world. And now you are evolving any particle, any falling particle, any orbiting satellite, any planetary orbit. These are simply all geodesics of this curved 4D space. This is finding, okay? The thing is that any falling particle, an orbiting satellite, planetary orbit, these trajectories are all simply geodesics, right? It's the exact same concepts of the curved 4D space. What's the source of the curvature is the mass of the sun, right? This is the sun, and any orbit looks like an ellipse, right? Newtonian mechanics recognize that it's an ellipse. But it's not pure ellipse. From time to time, over centuries, this ellipse rotates a little bit. Okay? This angle, we call it precession angle. Newtonian mechanics alone could not predict the precession angle. But Newton had to account, say, it's okay, if you have here the Mercury, for example, orbiting the sun, if you account for Mercury and sun, according to Newton's equation, you will not get precession. But physicists, they observe precession for sure. So you had to add, oh, this guy is also affected by the other planets. When you include the effect of the other planets, Newtonian mechanics alone get the precession. Okay? For all the planets except the Mercury. Because the Mercury is the closest one to the Sun, right? So for the Mercury, there was this anomaly in its orbit that is not illustrated or explained by Newtonian mechanics for decades. Now, the precession, this angle, the precession of the Mercury, you Google precession of Mercury, you'll find this, is about 566 seconds. We're talking about very slight precision, seconds. Seconds as a unit of angle, okay? Per century. Newton, using the effect of other planets, got something like 5557, which is great accuracy, right? Second per century. But there was that about particularly 42.5 seconds per century not captured by Newton. Okay? Do whatever you like. You will not capture this. When Einstein applied this crazy idea, what is that? That the mass of the sun bends the space-time world, and your trajectory, he used differential geometry, he used this. Your trajectory is simply a geodesic on the kinetic energy Riemannian metric mean. Okay? No effect of other planets, I don't care. What he get for this thing? 43. So this was his celebrated result. Out of the observed 42.5 seconds per century, he got 43 seconds per century.
0.5 as well.
Yeah, so with a great accuracy. I mean, confirming his result. And recently we had another confirmation for the gravitational wave.
Doesn't the mass of the other planets also affect the geometry?
But with respect to, yes, you're right. With respect to the huge mass of the sun, is almost negligible. There is a very cool video that a guy brought. There's a sheet, okay, just talked, with a huge mass in the middle, and just throw a bunch of masses. They are orbiting the initial mass, and doesn't. So the initial huge mass immediately curved the sheet, right? But when you throw a bunch of other masses with respect to this huge mass, they don't affect the curvature anymore and just keep revolving, okay? Yeah, we're done. So, it's a long way with dynamics, analytical dynamics, calculus of variations, geometric mechanics in order to reach this point, to appreciate what Einstein did. Yeah. Thank you. And your final, some people didn't like the proposed Thursday, so we'll stick to the Tuesday at the same time. You will come to my office, you'll find your copy of the exam. You'll take your copy and return it the next day at the same time. Yes, Mikhail?
Could we have more time to return it? Basically because we have an exam, the 206 exam. So
No, we can agree on whatever time, but it has to be 24 hours. So we can agree on whatever initial time. When you guys want to start. I'm fine with Monday, Tuesday, Wednesday, Thursday, Friday.
Friday.
Yeah, actually you will need to return the Saturday. If you're okay, if the majority are okay with that, not the majority, everybody.
How about Wednesday? Because we have the test on Tuesday. So how about Wednesday and
So, is anybody here agrees with Wednesday, the time of the exam? Anybody here who has an objection with Wednesday? You?
Okay.
Yeah, sure. Okay, so Tuesday. Tuesday is the last option because it's the safe option. It's already there. Thursday, people already showed that they don't like. Friday, anybody doesn't like Friday? Yes. So Monday, of course, Monday people will not like it because it's too soon, right? Okay, so it's Tuesday also.
yeah, time 10:30.
10:30, and you will return at 10:30 the next day. I will send you some survey, very short, just 2 questions actually, on what you like and what you didn't like, so that we can remove some stuff from next year. Professor, yeah.